going to take a look at secants, tangents, and angle measurements when specific scenarios arise. So, little review, a secant is a line that intersects a circle in exactly 2 points. When they intersect within a circle, the angle formed are related to the arcs they intersect. So, secant is a line that cuts through in 2 points. A chord is a line that's kind of like diameter, runs from one end to the next, but it's within the circle and not necessarily within coming within the center of the circle anyway. So if I have two secants or chords intersecting in the interior of the circle, the angle formed is half the sum of the measures of the arcs intercepted by the angle and its vertical angle. So then vertical angles are across from each other. So notice in red on the figure to the side, angle 1 is in red, and then arcs AB and CD are in red, and then 2 is light blue, so arcs BC and AD are light blue as well. To find the angle measure of angle 1, it's going to be half of arcs AB plus arcs CD. And then angle 2 is going to be half of arcs BC plus arc AD. So we can use this to our advantage in order to figure out the angles. Now again, we remember our rules. Central angles are the angle is the same measure as the arc it intercepts. Inscribed angles are half of the arc that they intercept as well. Whereas if I have two secants or chords that intersect somewhere within the circle, the angle created is half the sum of the arc it intercepts and its vertical angle. So what does that exactly look like? Well, according to our 4 examples here, it's relatively easy. I'm only going to do a couple of them. To find the angle measurement of x, notice our chords here do not necessarily intersect in the center of the circle. So here we have to use the theorem that we just learned. So our x is going to be equal to half of the arc it intercepts and its vertical angle. So if this is angle x, the vertical angle is directly across from it. So I need to know the measures of those two specific arcs. So the arc that is intersected by the angle with x, it is UVT. So we're talking about arc TU. And then the arc that is intercepted by angle RBS is arc RS. So it's going to be half of arc TU plus arc RS, which in this case, we already have the measures of 130 plus 84. Well, 130 plus 84 gives me 214. And when I cut it in half, we get 107 degrees. So that is our angle measurement x, 107 degrees. Now, B is a little bit different. We are given an angle measurement of x degrees, but we are told about arc AB and arc CD. That's not what we're looking for. We need arc BD and arc AC. Now, what we can do is use our general knowledge of circles in order to figure out exactly how much is left over for these two specific arcs. We know a circle is 360 degrees. So if I know these two parts, if I take them away from 360, I am left with whatever AC and BD happen to add together. So that's going to be step 1. Step 1 is 360 minus 143 minus 75. And when I do that, so 360 minus 143 minus 75, we get a total value of 142 degrees that is left. So 142. So that means arcs AC plus BD end up adding to be 142. So to find x, it's going to be half of that measure, which ends up being 71 degrees. So letter C here is the same as A, where we're given the angle measurement and the appropriate arcs that we need. and D is the same thing as B, where we're given an angle measurement of X, and then two arcs that are not necessarily what we need, but we can subtract them from 360, and then cut the answer in half to get the value of X. Now another theorem we have is if I have a secant and a tangent intersecting at the point of tangency, the measure of the angle formed is half the measure of the intercepted arc. So again, secant is a line that starts on the circle and runs through it. So we have our 2 points, and then tangent is a line that just touches the circle in one specific spot. The angle formed by the scenario is half of the intercepted arc. So 1 is going to be half of arc AB, and angle 2 is going to be half of arc ACB. Not ABC, ACB. And we can use that to figure out. Now here we have to find the measure of angle QPR. So QPR is here, and based on this theorem, it's going to be half of the intercepted arc. So intercepted arc is PR, so it's going to be half of arc PR, which is half of 148, which ends up being 74 degrees. So angle QPR is going to be 74 degrees. Now B asks us to find the measure of angle DEF. Now we don't necessarily have angle DEF on here, but we do have point D to point E, and then we have point E through point F. So this is our unknown angle X here. Now here we have the secant DF and tangent DC, when we learned that the angle is half the intercepted arc. So if angle D, or angle CDF is 64, that means arc DF is going to be twice it. So 2 times 64 is going to give me my arc FD. So that's 128 degrees. Now DEF is actually an inscribed angle, and we learned previously that inscribed angles are half of the intercepted arc. So DF being the intercepted arc, so angle DEF is equal to half of arc DF, which is half of 128, which ends up being 64 degrees as well. So angle E is going to be 64 degrees. Now let's say we have a theorem, let's say we have two secants, a secant and a tangent, or two tangents intersecting in the exterior of the circle. So this time we're on the outside. The angle that is formed is going to be half the difference of the intercepted arcs. So for our first one, angle A is going to be half of arc DE minus BC. For our second one, again, it's going to be the intercepted arc, so angle A is going to be half of arc BC minus BC. And last but not least, let's say we have this one, again, angle A is going to be half of arc BDC minus arc BC. So again, if it's on the outside of the circle, we're going to be subtracting. Again, the point of intersection creating the angles. And if the point of intersection is on the inside, the angle measurement is going to be half of the sum of the intercepted angles, or sum of the intercepted arcs and the arc with the vertical angle as well. So this one, we need to find the different angle measurements. Let's say we want to find angle L, and we are told we have arc HK being 102 degrees. Well, first things first, I need to know the measure of the arcs that are intercepted. Fortunately, we have a full circle here being intercepted. We know a full circle is 360 degrees. So, if this part is 102 degrees, to find the rest of it, we just subtract it from 360. So 360 minus 102 is going to give me arc HJK, and this will give me 258 degrees. So HJK is 258 degrees. And to find the measure of angle L is half the difference of these two. So 1/2 of 258 minus 102. Well, 258 minus 102 is 156. And then we just cut it in half. So 78 degrees. And we can also go backwards. If we're given an angle measurement and an arc, we can find the missing arc. So here we're told angle A is 56, BC is 95, and we need to find CD. So again, the theorem states the angle is equal to half of the larger arc, in this case DC, minus the smaller arc BC. So the angle measurement is 56 degrees, so that's going to be half of our unknown x minus 95. So if we're dividing by 2, like we are, we're cutting in half, so we divide by 2, meaning we have to multiply by 2 in order to cancel out our fraction. So times 2. So the half and the 2 will cancel out. 2 times 56 gives me 112. Gives me x minus 95. Now what we'll do is we'll add 95 to both sides. So the 95s will cancel out, leaving us with just x. And then we add 112 and 95. So we get 207. So that means arc DC is 207 degrees. Then we can use what we've learned so far, inscribed angles, intersecting on the outside. We can figure out measures of angles within circles in a more complex figure like this. Find x, y, a, b, and or c. Here we're given angles a, b, and c, and solid measurements of 52 degrees and 34 degrees. So what we want to do is we want to start labeling off things that we know. So here we have an inscribed angle at point C of 52 degrees. We know inscribed angles are half the intercepted arc. So B to D is going to be double 52. So 52 times 2 means arc DB is 104 degrees. Same with down here, we are told we have a chord and a line tangent creating 34 degrees. When I have that scenario, again, the angle formed is half the intercepted arc. So this means B to C is twice 34. So it's going to be a 68 degree arc. So now that I have arc BC, I notice that angle A is comprised of that intercepted arc. So here the angle being an inscribed angle, so angle measurement of A is half the intercepted arc, which in this case is 68 degrees, which ends up being 34 degrees. So the measurement of angle A is 34 degrees. Now if I look at our angle up here at C, again C is comprised of points D, E, B. Again, it being an inscribed angle, we know angle C is going to be half of the intercepted arc, so the arc BD is 104 degrees. So we take half of 104. So we end up getting 52 degrees. So now what I need to do is I need to figure out exactly what is angle B. So first things first, is there anything else that we can really figure out what's going on here? So we have 68, 104. We have inscribed angle of angle B, so we need to figure out exactly what is arc EC. So how are we going to do that? Well, we know for a fact if we have a line of tangency running through a diameter, we can create this angle. However, we can go an even simpler route. Because we know BE is a diameter, and again, we know it's a diameter because it runs through our center A. So BAE is our diameter. We know B around to E is going to be 180 degrees, which means D to E. So if I take arc BD and add DE, I'm going to get 180. So to figure out DE, I take 180 and I subtract 104. And I get 76 degrees. So arc DE is going to be 76 degrees. And now that I know 3 out of the 4 sections, all I have to do is subtract these 3 from 360 to figure out EC. So arc EC is equal to 360 minus 180 minus 68. And again, we know it's 180 because half a circle is 180. So here's our 180 degrees, and then 68. So 360 minus 180 minus 68. So we got 112. And again, angle B is an inscribed angle, EDC. Inscribed angles are half of the intercepted arc. So angle B is going to be half of 112. And we end up getting 56 degrees. So again, we can use everything we've learned so far in regards to circles, inscribed angles, diameters, arcs, intersecting with secants and tangents to figure out angle measurements and arc measurements as well. Now number 2 is a little more fair. We're given tangent DB, we're given radius AB, radius AC, chord CB. We got to find angle B, we need to find angle A, and we're told DBA is 106 degrees. So first things first, in order to help us figure things out, we're going to start marking up what we know. Now we know the measure from, I'll label this as point E, so that we're there. So we know that E to C is going to be 180 degrees. However, here we have a line of tangent with we have a chord and a tangent intersecting with a measurement of 106 degrees. So we know that arc BEC is going to be twice that. So again, the angle measurement is half of the intercepted arc. So if I know the angle measurement, I have to multiply it times 2. So arc BEC is going to be 2 times 106. So arc BEC is going to be 212 degrees. So because we know this part, CB is going to be the remainder of it. So a full circle is 360. So arc CB is going to be 360 minus 212. So arc CB is going to be 148 degrees. Now the angle measurement of B there, we know it's a central angle. And we know it's a central angle because we are given point A as the center. And central angles are the same as the intercepted arc. So angle measurement of B is created by the angle CAB, which the intercepted arc is 148 degrees. So angle B is going to be 148 degrees. Now, where do we go from here? Because everything is pretty much threadbare. We're given angle measurement of A, and the only true number we have in our triangle here, created by points A, B, and C, is 148 degrees. Well, fortunately for us, I know that A to B is a radius. Again, we know point A is the center because lines run right through it, point A being the center. So A to B is a radius, and every single radius within a circle is going to be congruent. So A to B is actually going to be congruent to A to C. So we actually have what's known as an isosceles triangle here. An isosceles triangle is when I have a triangle with two sides that are the same. The isosceles triangle theorem states when I have two angles the same, the sides opposite or across from those angles are going to be congruent. We can also go backwards. If I have two sides that are the same within a triangle, the angles that are opposite or across from it are going to be congruent as well. So here we have two sides. So here we have angle A being congruent to, we have angle A leading to side AC, and the angle over here at point C leads across to the radius AB. Because they are both the same, I can also designate this angle as A, because they are going to be the same. Now here I have two A's with 148. I know for a fact that triangles add up to 180 degrees. So if I take angle A plus angle A plus 148, I'm going to get 180 degrees. So here I have two A's plus 148 gives me 180. I'm going to subtract 148 from both sides. So I get 2A equals 180 minus 148, and I get 32. So we'll divide by 2 now, and we get A equals 16 degrees. And that's what we're looking for. So we get angle A is 116 degrees, and we got angle B to be 148 degrees. So again, took a little bit of thinking, realizing what we know, stuff we've looked at in the past concerning triangles, and determining our values. So that is secants, chords, tangents intersecting within and outside a circle. Again, if chords and secants or chords and tangents are intersecting within the circle, I'm going to add the vertical arcs and cut in half to get the angle measure. If our points of intersection are on the outside, I'm going to subtract the bigger intercepted arc and the smaller intercepted arc and then cut it in half. So again, chords and secants intersecting inside, I add the vertical arcs, cut in half. If the point of intersection is on the outside of the circle, I subtract the intercepted arcs and then I cut in half.